Okay, so let's look at the common I/O interface. Okay, so there are three common I/O interface available. Okay, one we call it as an elementary I/O. Okay, which is it is a simple two-state device such as LED and switches. Okay, so the elementary I/O is actually a simple input-output device. Okay, which is it only have two states, either on or off. Okay, either on or off, or logic 1 or logic 0. Okay, so that is what we call it as a elementary I/O. Okay, so example here is such as a LED. Okay, so your LED, you can turn on your LED, you can switch off your LED, or you have a switch. Okay, when you press the switch, okay, the switch will give you a logic high, or when you release the switch will give you the logic 0. So this is what we call as a elementary I/O. Then we have a parallel I/O. Okay, which is this parallel I/O, the data exchange one byte at a time. Means that you send a data, okay, from input to output parallelly. Okay, if you have a 8-bit data, so you send out the 8-bit data at the same time. Okay, so that what we call as a parallel input output. And then last but not least, we have the serial input output. Okay, which is the data exchange one bit at a time. Okay, means that even though you have an 8-bit input, but you only can send out one bit at one time. Okay, so that's why we call it as a serial I/O. Okay, next we go to the Atmega 32 input output port. Okay, as we already learned in the previous class, okay, we have a total of 40 pin out in our Atmega 32. Okay, from this 40 pin out, 32 pins are dedicated to our input output port. Okay, so a total of 32 pins is dedicated to input output. Okay, to your I/O. Okay, which is 8 pins are dedicated to port A, and then you have a port B. Another 8 is for port B. 8 bit or 8 pin is for the port C, and another 8 pin is for port D. Okay, and then what about the rest of the pin? Okay, the rest of the pin is used for the reset, for your VCC, ground connected to your oscillator. Okay, and then you have a VCC and RF. Okay, so most of the pin in Atmega 32 is dedicated to use for input output. Okay, so this, okay, what about the 8 remaining here? Okay, the other 8 remaining 8 pin, okay, the other remaining 8 pin is used for, okay, so every time you see the pin marked with GND, so means that you need to connect this GND to your ground. And if you see the VCC and AVCC, okay, so VCC and AVCC, you need to connect it to your 5-volt. Okay, and then you have a reset. So this reset pin is also high, but we usually prefer to put a switch at this point for the reset of the chip. Okay, so you need to put a reset, okay, a switch, which is whenever you press the switch here, it will give you a logic 0. Okay, so this is for the reset function. Okay, and then the rest of, then you have an external, which is you need to connect it to your oscillator and your RF. Okay, so your RF is used actually for the voltage reference if you're going to use analog to digital converter. Okay, so let's look at the I/O port register. So this one here, we already learned in the previous module as well. Okay, so since you have 4 ports, port A, port B, port C, and port D, each of the port here have 3 registers. Okay, which is a DDR port X register and pin X register. So what this register do? Okay, for the DDRX, this register is used to determine a given port. Either you are going to use it as an input port or as an output port. So how to do that? Okay, you need to do a certain programming to your DDR. Okay, if you put 0 to your DDR, then what happens? Your port become an input port. If you put 1 to your DDR, then it becomes output port. So this is the use of the DDR, which is a data direct register, which is you're going to determine or you're going to initialize. Either you're going to make your port as an input or as an output. Then we have a port X. Okay, so when you initialize your port as an output, that every time you're going to send out the data from micro P to your output, so we need to use the port X register. Okay, which is this port X register is used to send the data out to your pin. Okay, or to your outputs. Okay, when you initialize your port as an input port, so what happens is, in order to read a data from outside or from your input device, okay, and then set it to the microprocessor or to your CPU, we need to use the pin X register. Okay, which is this pin X register used to read the data present at the pins. Okay, so this is your Mega 32. Okay, you have a total of 8 pin out for each of the ports. Okay, so this is the pin, and each of the port has a 3 register associated with input output, which is a DDRX, port X, and pin X. Okay, so now we are going to see how to write a program in C for the I/O. Previously, we already learned about how to do a I/O programming by using an assembly language. Now you're going to see how to do I/O programming by using the C language. Okay, so first sequence, what you're going to do here is we need to know how to write a C program in order to initialize our input-output port, so that we can make our I/O port either as an input port or as an output port. Okay, so how to make I/O port as an input or output? So in order to make your I/O port as an input or output, so you need to initialize on your DDRX register. Okay, for example here, okay, to make a port as an output, so what are you going to do? Okay, you have a DDR. Okay, if you're going to make it as an input, so what you're going to do? Okay, you need to write 0 to your DDR. If you're going to make it as an output, okay, you're going to make your port as an output. So what you're going to do? You need to write 1 to your DDR. Okay, the question is how to write this number here, either 0 or 1, to your DDR by using a C programming. Okay, so earlier, okay, we already learned how to make it in by using the assembly language. Okay, so for example here, okay, you're going to make your port B as an output. So to make a port B as an output, so what you're going to do is you need to put 1111 to your DDR-B. So this is your DDR-B. Okay, so DDR-B consists of 8 bits. Okay, now you're going to make your port B, the whole port B as an output port. So what you're going to do, you need to put 1111 to your DDR-B. Okay, earlier, okay, we already learned how to do it by using a assembly language, by using the LDIR16OXFF, which is 11111. Okay, so this is FF. Okay, if you convert this binary to hexadecimal, then you get the FF, and then out DDR-B R60. So this is by using the assembly language. Okay, now you're going to make it by using the C programming. So how to write in a C programming? Okay, it's really simple. Okay, so you just use the DDRB. Okay, and put the equal and what number that you're going to send out to your DDRB. So in this case here, 0x at x, and then put the semicolon. So this is how you're going to initialize your port B as a output port. Okay, what about if you're going to initialize your port C as a input port? Okay, so to initialize your port as an input port, so what are you going to do? Okay, you need to write 0. Give 0 to your DDR register. Okay, for example, okay, make port B as a output port. So to make a port B as a, so this one here, please change this one output to input. Okay, so what are you going to do? Okay, so you have a DDR, so this is your DDRB. Okay, so now you're going to make the whole port B as a input. So what you're going to do? Okay, you need to send 0 or write 0 to your DDRB. Okay, so this is a 0, 0, 0, 0, 0, 0, 0. So after you put this 0 here to your DDRB, so what happens is your port B become input port. Okay, so how do we do it in assembly language? Okay, to do it in assembly language, you simply load this number here to your GPR and then send out the number that you load to this GPR to your DDRB. So this is why you did the assembly language. So now you're going to, yeah?
In previous chapters, we learned how to make the both as input and output at the same time. Can we do the same here?
Yes, we can do the same. Okay, in the next slide, we will see how to combine an input and output at the same time.
Okay, thank you.
Okay, so how to do that? Okay, you just simply write DDRB. Okay, so because you're going to make your port B as input, so DDRB equal to, so what number that you're going to send out to your DDRB? Okay, since this one is 0, so simply write 0. So what happens? Followed by semicolon. So what happens after you execute this line here? So now your port B become input port. Okay, so this is how you're going to write in string language. Okay, so you see the difference. Assembly language, you need two lines of instruction in order to initialize your port as an input or output port. But for the string language, you only need to have one line of code or one line of instruction to do that. Okay, so this one here, okay, so this is a summary. Okay, to access a port register as a byte, okay, you're going to use the port X label, which means that every time you're going to send out the data from CPU to your output, so you need to use the port X register to do that. Okay, if you're going to initialize your port, either you want going to make it as an input or as an output, okay, you need to use the DDRF register. And if you're going to read the data from your input port, okay, and then take the data to your CPU, then what you're going to use is you need to use the pin X register. Okay, so let's look at these examples here. Okay, so you have an LED that are connected to pin of port B. Okay, so we just draw the Atmega 32. Okay, so this is your Atmega 32. And then this is your port B. Okay, and then this port B here is connected to your LED. Okay, you have an 8-bit of what we call here port B. All of these 8-bit port B are connected to your LED. Okay, so now you need to write a C program that show the count from 0 to FF on the LED. Okay, so you need to do a counter, which is this counter here will start counting from 0 to FF, or from 0 to 255. And this counter here will be displayed on this LED. Okay, so first, what you're going to do is we need to identify what type of LED that you're going to use. Okay, because we have two types of LEDs here. Either you're going to use a common cathode or common anode. Okay, and then the value that you're going to set out to LED will be different if you use the common cathode or common anode. So in this case here, we are going to use a common cathode. Why I say that this one is common cathode? Because all the negative terminal of LEDs are connected to ground. So that's why we call it as a common cathode. Okay, so for the common cathode, okay, how to make the LED turn on and turn off? Okay, because this is your LED. Okay, so this LED is connected to ground. Okay, and then this will go to your micro-P. Okay, so this is your micro-P. Okay, how to make this LED turn on? Okay, to make the LED turn on, since this is a ground, okay, so the ground is a logic 0. Okay, if you put 0 to your micro-P, what happens? Okay, this 0, okay, from micro-P you have a 0, and this also 0, so no current can flow. So what happens when no current flow? The LED will turn off. Okay, so means that if you put 0 at your micro-P, okay, LED will turn off. Why? Because this is a logic 0, and this also the ground is a logic 0. No current can flow, so it will turn off. Okay, what happens if you put 1 at your micro-P side? Okay, so this is your micro-P, you put 1 at your micro-P side. So what happens? Because this is a logic 1 and this is a logic 0, so you have a high here and this is a low. So what happens? The current can flow from high to low. So what happened here? So now, since the current can flow from high to low, now your LED can turn on. Okay, your LED will turn on. Okay, because of the logic that you put to your LED. Okay, from this micro-P. Okay, so that's why I'm telling you that the common configuration that you're going to use here is crucial. It's very important in determining what are the values that you're going to use in order to make it a turn on or turn off. Okay, so let's look at this one here. Okay, so you have a LED that are connected to port B. Okay, then you're going to write an AVRC program that shows the count from 0 to FF. Okay, so you're going to make a counting sequence, which is it will count from 0 to FF or from 0 to 55. Okay, and this counting will be shown to your LED. So how to do that? Okay, the first thing first, what you're going to do is, okay, so you need to write this header here. Okay, hashtag include avr/io.h. Okay, so this one here actually similar to .include amplitude.inc in assembly language. Okay, so this is the equivalent. Yeah? Hashtag include avr/io.h is actually equivalent to .include, okay, amplitude.inc in assembly language. Okay, then after that, okay, you can start with your main program. Okay, this is your main program. Started with your main program, int mainboard. So this you're going to start your main program here. This is your main program. So inside of your main program, you need to write all the tasks or all the programs that you're going to solve in this example 7.9. Okay, so this is your main program. Okay, so first, what are you going to do? Okay, inside of your main program, okay, first, because this port B is connected to LED, so what are you going to do? Okay, we need to initialize our port B so that the port B become an output port. So how to do that? Okay, you need to initialize at your DDRB. Okay, so what value that you're going to send out to your DDRB? Because this is the output, so the value that you're going to send out to your DDRB is 1. Okay, since 8 LEDs are connected to port B, so the value that you need to put, okay, to send out to your DDRB so that the port B, the whole port B become output port is FF, or 111111 in binary number. Okay, so that's why DDRB equal to OX FF. Means that you're going to make your port B as a output port. Okay, then after that, what are you going to do? Okay, then after that, we can start to the counting sequence. Okay, we can start counting. Okay, so in this case here, we use the while one. Okay, what is this while one do? Okay, so what this while one do? This while one is actually you're going to do the same thing continuously. Okay, so this means that you're going to do the whatever inside of this while loop here continuously. Okay, or forever. Okay, so in this inside of the while loop, what you're going to do? You're going to do the counting, which is you're going to start a counting from 0 to FF, and then send out the value to your port B. So how to do that? Okay, just simply port B equal to port B plus 1. So this port B here will keep increasing, okay, 1 by 1. Okay, started with 0, and then it will go to 1, and then followed by 2, 3, 4, until 255. Okay, and then put a return 0. Okay, and this is the solution. Okay, how to write a program, okay, to do a counting sequence, which this counting sequence will be sent out to port B and to port B to display to your LEDs. Okay, so this is how to do the okay, how to initialize the input output port and how to use the port X register. Since this is a output port, okay, so we need to use the port X register. And if you initialize your DDRB as an input port, then you need to use your pin X register in order to read the data. Okay, next. Okay, you're going to selecting the direction of a pin. Okay, means that, okay, one of your friends here asking, can we combine in the same port? Can we combine the what we call a combination of input and output at the same time? Yes, you can do that. How? By selecting the direction of your pin. Okay, so for example, okay, let's show examples here. Okay, you're going to make pin 7 to 4 of port B as an input, while the rest of pin as a output. Okay, so you have a port B. Okay, so this is your port B. Okay, you have a 8-bit of your port B. Okay, so this is a pin 0 and this is your pin 7 and pin 0. Okay, now what you're going to do here? Okay, according to this example here, pin 7 to pin 4, okay, you're going to make it as an input, while 0 to 3, okay, you're going to make it as an output. So we have an input and output ports at the same time. So how to do that? Okay, similar to what we did earlier. Okay, we need to initialize, okay, this input output on our DDRB. register. Okay, so as I mentioned earlier, okay, to make an input port, so you need to give a 0 and give 1 if you're going to make it as a output port. Okay, so input is 1. Okay, input is 0 and output is 1. Okay, so since this one here, okay, so this is an input. So what you're going to do here is you need to put 0 lah kat sini. So 0, 0, 0, 0 on your DDR bit. What about this one here? You're going to put 1, 1, 1, 1 because this is a output. So how to write in the C programming? Okay, DDR bit equal to OX 0 F. Or if you don't want to write in a hexadecimal, okay, you can simply write in binary number. Okay, 0 bit. Okay, the first 4 bit here. Okay, you put 0, 0, 0, 0. So you know that this is a input port and followed by 1, 1, 1, 1. So this is your output port. Okay, so this is how we're going to initialize a combination of input and output at the same time on the certain ports. Okay, for another example, okay, make odd pins, okay, which is pin 7531 of port C as an input, while the even pin 6420 as an output. Okay, again, how to do that? Okay, you need to initialize on your DDR register lah. Okay, so DDR-C, so this is your DDR-C. Okay, you have 8 bits of DDR-C. Okay, so this is 0, 1, 2, 3, 4, 5, 6, and 7. Okay, so odd pins, you're going to make it as an input. So this one is an input. All the odd pins here as an input, while the even pins, okay, the pin genap here as an output. So what are the values that you're going to put inside of your DDR-C? So this is an input. Input, you need to put 0. Output, put 1. So this is the value that you're going to put to your DDR-C. So how to write the program? Just simply write DDR-C equal to 0B. Okay, so just use a 0B lah. Easier for us. Okay, by using the binary number instead of hexadecimal, because if in hexadecimal you need to convert this number to hexadecimal then put it inside of your program. Okay, so this one here is a 01, 01, 01, 01, and 01. Okay, so now what happened here after you execute this line? So what happened? Odd pins will become an input port, while even pins will become an output port. Okay, any question up until here? Ada soalan tak? Okay, if no question, then we go to the next slide. Okay, now we're going to see the pull-up resistor. Okay, so there is a pull-up resistor for each of the AVR pins. Okay, so means that the whole pins inside of your AVR have a pull-up resistor. Okay, so what does pull-up resistor do? Okay, so this pull-up resistor is useful to reduce noise. Okay, so since input of the AVR are generally in high state, so those make them prone to catching noise and picking up false signal. So the rule of thumb, okay, if you're going to enable or you're going to disable the pull-up resistor, the rule of thumb here is, okay, every time you use the port as an input, then you need or you must enable your pull-up resistor. Why? Because you're going to reduce noises. Okay, if you're going to use your port as an output, no need to enable your pull-up resistor. Okay, input must enable pull-up resistor. Okay, how to enable the pull-up resistor? Okay, to activate the pull-up resistor, okay, you're going to put 1 to your port X register. Okay, so how to enable? Okay, you have a port X register, put 1, enable for your pull-up resistor. If you put 0, then you disable your pull-up resistor. Okay, so to deactivate the pull-up resistor, just put 0 into the bit of the port X register. Okay, so why are we going to have this pull-up resistor enable or disable? Because you're going to reduce. Now, so every time you use your port as an input, make sure you enable the pull-up resistor. Okay, so let's look at this example here. Okay, so this example of code is without a pull-up resistor. So if you see this at the top, okay, you have two versions of codes here. At the top here, it is written in the assembly language, while bottom is written in the C language. Okay, so let's look line by line. Okay, dot include m62def.inc. So this one here actually this line. Okay, so this is equivalent. Okay, hashtag include abr/io.h. Okay, and then you have, okay, so this is your main program. So in C programming, okay, you need to have your main program. Okay, all the program must be inside of this main program. How to start your main program? By using the int main void. Okay, so every time you're going to start your main program, make sure that you put it inside of this function here, int main void. So all the main program must be inside here. Okay, and then now you see here, load IR16 0x00 out DDRC R16. So you know that you're going to make your port C as a input port. Okay, how to write it in by using the C programming? Just simply write DDRC equal to 0. Okay, so this is the second one. Okay, this is first. Okay, and then load IR60 OXSS out DDRB R60. So what happens here? You're going to initialize your port B as a output port. Okay, so this is number 3. Okay, how to do it in C programming? Okay, so just simply DDRB equal to OXSS. Okay, then we see this one here. In R60 pin C, load I R17 5 at R16 R17 out port B R16 R jump L2. Okay, you see there R jump L2. Okay, this loop is done forever. Okay, you continue to do this loops here forever. So what you're going to do in your C programming? By using the while loop. Okay, while one open curly bracket, close curly bracket. Okay, so that this loop will be done forever. Okay, or will be continued forever. Okay, next we see here in R16 pin C. So what happened here? Okay, you're going to read whatever the value from pin C and put it to your R16. Okay, put it to your register. Okay, in C programming, okay, we can simply put something like this. Okay, you initialize, you define a variable, okay, which is Z equal to pin C. Okay, before you use this Z here, okay, make sure you define this variable Z. Okay, how to define the variable Z? By using the unsigned char Z. If you not define this Z, either it's as a char or either it's as a int, okay, the Z, the variable data type. So what happen here? You might have a syntax error. Okay, so make sure that every time you use a variable, make sure that you define them first. Okay, so unsigned char Z and then Z equal to pin C. Okay, so this is a number 4 equivalent to this one here. Okay, load I R17 5. So put 5 to R17 and add R16 with R17. So what happen here? R16 sama dengan R16 tambah 5. something like that. Okay, so this is number 5. Okay, how to do it in C programming? Okay, Z equal to Z plus 5. Okay, so this is number 5. Okay, you see here, you need to 2 line of instruction to do this thing here, R60 equal to R60 plus 5, but this one here only need to have 1 line of instruction. Okay, then out port B R60 means that you're going to set out the value, okay, the result from R60 to port B. So how to do it in C programming? Port B equal to Z. So this is number 6. And number 7, this is number 7, and this is number 7, the Y. Okay, this is my, okay, you see here, okay, you have 2 ports. One, you initialize it at an input port. The second one, you initialize it as a output port. But for the input port, you not enable the pull-up resistor. Okay, so how to enable the pull-up resistor? Okay, from the same examples here. Okay, now we're going to enable the pull-up resistor on our port C. Okay, so in C programming, to enable a pull-up resistor, okay, you see here, you need to load this value, load I R60 or XFS, and out port C R60. What about in C programming? Okay, just simply add this line, port C equal to or XFS. This is how you're going to enable the pull-up resistor at your port C. Why port C? Because you initialize your port C as an input port. Since you initialize your port C as an input port, you must enable the pull-up resistor in order to reduce noise. Okay, so this is how to enable the pull-up resistor. Any question up until here? Okay, the rest of the the rest of the program similar to what we did here. Only that this one, okay, we have this line to enable the pull-up resistor.
Excuse me, Doctor.
Yeah.
Why we use port B and port C for only R16? Why didn't we use R16 and R17 for both port C and port B?
Okay, this one. Is it this value here? Okay, you can use the R16 or R17 or any register if you like.
No, I mean like for port B, I use R16 and port C, I use R17, or it must be in the same register.
No, you can use any register.
Okay.
Okay, as long as the register, because this is a load I, as long as the register is between R16 and R31, then you're good to go. Okay, you can use that. If you use the R0 to R15, then it's wrong lah. Okay, for the LDI. Okay, in this example here, okay, you can simply, okay, why not I use the R16 for the port B and R17 to port C. Also can. Okay, it depends on you lah, or on the programmer. Okay, whether you're going to use the same register or you're going to use the different register. Okay. Any other questions? Okay, if no question, then
Doctor?
Yeah.
I didn't understand the unsigned character in the previous example.
Which character?
Unsigned character, yeah. I didn't get what you said about it.
Okay, this one here. Okay, do you already watch the video that I give you earlier?
For chapter 9?
Yeah, for the chapter 9. Okay.
No, Doctor.
Okay, because this one here, okay, every time you use the what we call a variable, okay, you need to define your character. Whether you're going to make it as a 8-bit data, 16-bit data, or etc. So this is a must. If you not define your data type, so what happens is the C compiler will have some syntax error.
Okay.
Okay, so that's why every time you use the variable, okay, you need to define the data type. Either you're going to use a 8-bit data, 16-bit data, 32-bit data, depending on you. Okay, so this is the data type lah. Okay, you have a chart, int, long, float, and double. Okay, but for ArcMega32, okay, we only have a 8-bit, so this is the data type that we commonly use lah. Okay, either unsigned chart or chart. Okay, either a positive number or negative number. Okay, that's it.
All right, thank you.
Okay. Okay, so this is another example. Okay, we have a lot of examples in this slide here. Okay, so this example how you're going to configure your port, either to make it as an input port or output port. Okay, so let's look at the first line here. DDR8 equal to OXFF. So means that since you put 1 to your DDR8, so what happened here? The whole port A, you initialize it as a output port. Okay, and then DDRB equal to 0. So what happened? Okay, so this is your DDRB. Okay, DDRB is 8-bit, and then you put a 0 in your DDRB. So what happened here? So all of the port P's, you make it as a input port. Okay, now DDRC equal to OXF0. Okay, so DDRC, so this is your DDRC. Okay, so F0. So what is F0? So F is 1, 1, 1, 1. What about 0? 0, 0, 0, 0. So what happened here? Okay, so this one here become output port, and this one become input port. Okay, so this is the most important lah. Okay. Okay, the most important part here is in order to determine either you're going to make it an input port, output port, or a combination of input and output at the same time, you need to make it in your DDR register. Okay, another example. Okay, you're going to do a quick toggling all 8 bits of port B forever. Okay, you're going to do the toggling. Okay, port B forever with some time delay between on and off state. Means that between the toggling state. Okay, 0 go to 1, 1 go to 0. Okay, so what are you going to do? Okay, first, we draw the ArcMega32. Okay, so this is your ArcMega32. And this is your port B. And this port B here now, you're going to do a toggling. Okay, all 8 bits. So all 8 bits here, you're going to make a toggling. Okay, what is the toggle mean? Okay, means that if your first number is 0, 0, 0, 0, 0, okay, the next number should be 1, 1, 1, 1. Means that you toggle from 0 to 1. Okay, then the next sequence, what would be the value? 0, 0, 0, 0 again. Okay, means that 0 will toggle to 1 and 1 will toggle to 0. So this is what the mean of toggle. Okay, so how to write the program? Okay, so since this is a port B, so we need to identify either this port B become an input port or output port. Okay, since in this example here, okay, you're going to do a toggling, means that you're going to send a data to your port B. So this port B become output port. Okay, every time you send a data, means that you're going to make it as a output. If you're going to read a data, so means that you're going to make it as a input port. Okay, so what are we going to do? Okay, we start with #include avr/io.h. Okay, so this is the first thing that you need to write. Okay, include the header. Okay, you need to use the header that you're going to use. Okay, and then start with your main program. Okay, int main void. Okay, open curly bracket and close curly bracket down there. Okay, next, what you're going to do? Okay, we need to initialize this port B so that this port B become output port. So how to do that? ddrp equal to oxff. So what happens? Port B become output port. Okay, next, you see the word forever. Okay, means that you need to use a while loop. Okay, because we doesn't have any port to initialize, so now we're going to use a while loop. Okay, open curly bracket and close curly bracket down here. Okay, and what we're going to do? Okay, we're going to do a toggle to our port B. Okay, let the first number that you're going to use set out here is 0000000. Okay, so what you're going to do? Port B equal to 0B0000000. So this is the first sequence that you're going to send out to your port B. Okay, and then the second sequence here you're going to send out is this number. Okay, port B equal to 0B1111, which is you're going to toggle the initial number here. Okay, so that it becomes like this. Okay, but okay, we are not done yet. Why? Because in this what you call here as question here, it says that there is some time delay between on and off state. Means that there will be a delay between the first sequence and the second sequence. Okay, so that's why I put the delay here. Okay, so delay. So this is the delay subroutine and another delay subroutine. Okay, assume that this delay subroutine is provided lah. Okay, so we just use a delay, and this is the program. Okay, if you're going to use put a return 0, you can do that, or if you're not going and don't want to use write the return 0, so you can. Okay, no need to write the return 0. Okay, either you. Okay, there are two options here. Either you're going to use to write a return 0, or you not write the return 0. Both are correct. Okay, so this is the program. Okay, to toggle your port B forever. Okay, next, another example. Okay, write a program to perform the following. Okay, keep monitoring. Okay, so keep monitoring. This is the important information here. Keep monitoring the PB2 bit until it becomes high. Okay, so this is Omega 32. Okay, you have a PB2. Okay, so let's see if your PB2. Okay, you're going to monitor your PB2 until it becomes high. So every time you see the word monitoring, means that this one there is actually your input, your switch. Okay, so we just draw our switch here. So this is a switch. When you press this switch, what happens? It will produce logic 1. Okay, because keep monitoring the PB2 until it becomes high. So when you press this switch, it will give you logic 1. If you not press the switch, it always give you 0. So this is the meaning of the A here, item A. And when PB2 become high, write 45 to port C. Okay, you have a port C, so this is your port C. So what happens? If PB2 sama dengan 1, okay, send 45 to port C. Else, Okay, and then send a high to low pass to PD3. Okay, then you have another one here, PD3. Okay, what happened here? This is your PD3. So what happened? You're going to send low to high pass. Okay, so first you send a low, and then after that you send high to your. Okay, sorry, high to low pass. Sorry, yes, high to low pass, not low to high pass. Okay, so this is your PD3, high to low pass. So send one, and then after that, send 0 to your PD3. So this is what happens when PB2 1. Okay, when you press this switch here, you send 45 to port C, and PD3 send 1 and 0 at the same time. Okay, what happens is PB2 0. Okay, what happens when the PB2 equal to 0? Okay, so nothing. Okay, just send nothing. Okay, so now we're going to write down the program. Okay, how to write down the program? So first, input the avr/io file, avr/io.h. Okay, include this file here to your memory. Okay, and then start your main program, int main void, open curly bracket and close curly bracket down there. Okay, so now we have 3 ports here. Okay, PD3, port C, and PB2. Okay, so what we're going to do? Okay, we need to initialize all these ports so that we can use this port to send out and monitoring the data. Okay, so port C. What are you going to do to your port C? Is it you're going to initialize it as an input port or output port for the port C? Because you're going to send out the data. Send 45 to port C. So what happens to your port C? So you need to initialize your port C as a output. Okay? So DDRC equal to OXFF. Okay? Next, PD3. Okay. What about the PD3? Is it an input or output? You're going to initialize it as input or output? PD3. Anyone? Okay, you're going to send. Okay, see here. Send high to low pass to PD3. So PD3 also you need to initialize it as a output port. So we just simply write DDRT sama dengan OXFF. Okay, so I just simply make the whole port D as an output port. Ataupun, okay, you can do a select. Okay, you can just select the PD3 as an output. Okay, we should write this what we call it, this line here. Okay, DDRT equal to shift 1 to the left 3 times. Means that you put 1 to your PD3. What about the rest? The rest you just put 0. Okay, actually this one here, this is equivalent to DDRT equal to 0B0000 1000. So this is a big 0, 1, 2, 3. Only PD3 become output, the rest become input. Okay, you can choose either you're going to write this one here or this kind of programming, or you can simply make the whole port B or port D as a output port. Okay, next, PB2. Okay, what about PB2? Because you're going to keep monitoring, means that you put the switch to your PB2. So what are you going to do? Okay, so I just simply make my port B, the whole port B, as a input port. Okay, because even though the PB2 only connected to switch, so why not I make the whole port B as an input port, because the other support pin not connected to any input or output. So I just assume that the whole port B as an input. Okay, if you don't want to do that, okay, you can simply write this something like this. Okay, only port B, which is PB2, become input. Okay, DDRB equal to tilde. What is tilde to? You're going to invert. Okay, shift 1 to the left. How many times? 2 times. Okay, which is D is equivalent. Actually, D is equivalent to DDRB equal to 0B1111. 1011. Okay, you see here, PB2 only become the input, while the rest you make it as a output. Okay, you can either choose this one, this kind of programming, or this one, or this one. All of the programming is correct. Okay, so this one here, port B, port C and port D, I make it an output, and D is a port B, I make it as a input port. Okay, next, what are you going to do? Okay, since I have a switch here that are connected to my port B, so what are you going to do? I need to enable the pull-up resistor. So how to enable the pull-up resistor? Okay, by writing port B equal to OX FF. Okay, so this is because the whole port B I make it as an input port, so why not I just enable the whole port B of the whole pull-up resistor in the port B. Okay, if you select only PB2 as an input, so this is the thing that you need to write Okay, which is port B equal to 1, shift to the left 2 times. Okay, so enable pull-up resistor at PB2. Okay, next. After the initialize is complete, so what am I going to do? Okay, so I started with a while loop Why while loop? Because I'm going to monitor this switches forever, continuously. Okay, so inside of the while loop, we have the open curly bracket and close curly bracket down there. Alright, so then inside of my while loop, what I'm going to do? Okay, I need to check whether this switch is pressed or not. How do I know this switch is pressed or not? Okay, when the switch is pressed, okay, it will give this value PB2 sama dengan 0B0000 and 0100. Okay, it will give this value. Okay, when the switch is pressed, it will give this value. If switch is not pressed, so what happens? This is not PB2, this is a pin B. Okay, what happened to my pin B? So the value inside of my pin B will be 0000 0000. So this is your PB2, and this is a PB2. Okay, so now what I'm going to do? Okay, so I just use the if-else statement. Okay, so if pin B equal to 0B 00. Okay, so this value here, okay, which is when the PB2 is pressed. Okay, so when PB2 pressed. So what happened when the PB2 equal to 1? When PB2 pressed, okay, I'm going to send out 45 to port C. So port C equal to OX45. And then next, PD3. Okay, I'm going to send out this value here, high and low. Okay, so how to do that? Port D. Okay, first send the high value to your port D. DOB 0, 0, 0, 0, 1, 0, 0, 0. So this is high. Okay, PD3 equal to 1. And then next, low pass. Okay, port D 0, B 0, 0, 0, 0, and 0, 0, 0, 0. So PD3 equal to 0. So this is what happened. Okay, send one and then low pass. Okay, what else? Okay, nothing. So I just close the curly bracket there. Okay, so this is only valid if the PB2 is pressed. If the PB2 is logic 1. What happens if the PB2 doesn't give a logic 0? So else, open curly bracket and close curly bracket. Okay, so under this else statement, okay, no need to do it to anything because PB2, when the PB2 equal to 0, nothing happens. Okay, so I just put that and then next I close my curly bracket and close my main program. Okay, so this is okay. This is the programming. Okay, to monitor the PB2. Whenever the PB2 high, so it will send out this value to port C and port D. Any question up until here? Any question, guys? Okay, no. Okay, great. Okay, now we go to another slide. Okay, so elementary I/O. Okay, I think we can go quick on this slide here. Okay, so let's look at the elementary I/O introduction. So as I mentioned earlier in the early class, so elementary I/O is a two-state peripheral device which allowing two-state condition. Okay, you have a two-state condition, either logic 0 or logic 1, either off or on. So that's why we call it as a elementary I/O. Okay, so example of elementary I/O such as bulb, okay, which is the bulb can only either light on or turn off. Or you have a LEDs, you can turn on or turn off the LEDs, or you can have a switch. Okay, push the switch, it will give you logic high, or release the switch, it can give you a logic 0, something like that. So in SDR, it can involve more than one bit at a time. Okay, so this is only one bit. If you have a multiple bit, what happens? Okay, so another example is a BCD. What is a BCD? Binary code decimal or the 7-segment display. Okay, which is in 7-segment display, you have a 8 LEDs that are connected together. Okay, some of the LED will turn on, some of the LED will turn off. So that one also we call it as a elementary I/O. Okay, so what are the requirements? Okay, so the requirement for the elementary I/O is the bit signal can be written to the output device under a program control, and a bit signal can be read from the input device under a program control. Okay, means that if you want going to write or send a data from CPU to the output device, okay, you need to use the X register. Or if you want to read a data from input device to your CPU, you can use the pin X register. Okay, so that what are the device required? Okay, so this one here. Okay, in order what we call it to use it as an output, we can use a latch. Okay, which this latch is used to increase the number of an output, and buffer is used in order to increase the number of input. Okay, so this one here, we call it as a input-output expansion. Okay, so this is what we will learn in the last slide of this class. Okay, so example of an output device such as a LED. Okay, you have a bulb, relay, coil, 7-7 display. An example of the input device such as push button, proximity switch, rotor switch, BCD decoder, and etc. Okay, so let's look at the first elementary I/O that we usually use, okay, or commonly use. Okay, we call it as an LED. Okay, so this is a semiconductor device that converts electrical energy that into the electric color of light. So this LEDs here have two terminals. One is an anode, which is a positive terminal, and the other one is a cathode, a negative terminal. Okay, so how are we going to determine, or how are we going to identify which one is belong to anode and which one belong to a cathode if you have a LED? Okay, for the anode, which is the positive terminal, you need to see at the long leg. Okay, every time you see here, okay, you receive a LED. The LED will have two different legs. One is a shorter than the other one is longer. Okay, the longer one usually indicate that one is belong to a positive terminal. Okay, and while the shorter one belong to cathode or negative terminal. Okay, what about if both of the legs here, the LED leg is same? Okay, the length is similar. Okay, between anode and cathode. Okay, you can identify the positive and negative terminal by looking at the inside of this LED, which is for the positive. Okay, for the anode. Okay, it has a shorter end inside, while for the cathode it has a larger end inside of the LED. Okay, you look like the reflector, so you know that this belongs to the negative terminal and this one belongs to positive terminal. Or sometimes, okay, you have the flat surface on this side here. Okay, sometimes our LED come with something like this, so you know that this one is belong to negative terminal. Okay, so bear in mind that the LED is easily damaged by heat. So make sure that every time you're going to connect your LED, make sure that you need to connect to the resistor in order to reduce the amount of current that will flow to your LED. So this LED has a variety of colors here. Okay, from red, yellow, blue, green, and white. Okay, so never connect any LED directly to the battery or power supply. Why? Because if you connect the LED directly to the power supply, then your LED might be damaged. Okay, because of the two current flow to your LED and the LED become damaged. Okay, so the LEDs must have a resistor in series to limit the current. Okay, for a quick testing purpose, a 1 kilo ohm resistor is suitable for most LEDs if your supply voltage is 12 volt or less. Or sometimes we can use the 330 ohms resistor. Okay, that with the resistor value that you're going to use in order to limit the current that will flow to your LEDs. Okay, so how to determine the resistor value? Okay, so this one here, okay, you already learned in your theory lita, or okay, by using the V equal to IR. So this one here just for the recap, okay, will not come in the what we call here final exam or the microprocessor test. Okay, we will not cover on this part. This is just for the recap. Okay, and now we're going to see how to turn on an LED. Okay, so suppose you have an LED. Okay, so this is a LED. Okay, and this is your positive terminal and this is negative terminal. Okay, make sure that you know lah. Okay, your LED symbol and the terminal that, okay, the what we call it, the terminal for this symbol here, which one is positive, which one is negative. Okay, so this is your LED. Okay, the positive terminal is connected to 5 volt, and the negative terminal connect to your resistor, and then after that you connect to your micro P. So this is your micro P. Okay, to your micro P port, either port A, port B, port C, or port D. Okay, if you give this one is 5 volt, and this one here, at the micro P pin, you give 1. So what happens? Okay, since this is a high, and this also high, as I mentioned earlier, when high and high, there will be no current flow, okay, through your LED. So what happens when no current flow? LED will turn off. Okay, so if this high, okay, because this is a 5 volt high, and you give, okay, this is your micro P, and you give the output at your micro P is 0. So what happens here? Because this is a low, so now the current can flow from high to low. So what happens? When the current flow through your LED, the LED will turn on, and so in this case here, okay, to turn on the LED, you need to give 0. To turn off the LED, you need to give 1. So what happens if I change the, what we call here, the position of this LED? Okay, so now I have this something like this. Okay, so this is micro P. Okay, previously positive terminal is connected to VCC. Now positive is connected to micro P, while negative connected to ground. So what happens? So how to make LED turn on? Okay, since this is a 0, which is always low. Okay, if I give 0 here, what happens? 0 and 0, no current can flow, so LED will turn off. Okay, then if I give a 1 to my micro P, so what happens? Since this is a 1, so this is a high, and now current can flow from high to low. So what happens here? The LED will turn on. Okay, so the way that you connected to your LED to your micro P will decide what value that will turn on and turn off your LED. Okay, so this one here we call it as a common cathode or common anode. What type of a common configuration that I'm going to use to connect to your LED to micro P. Okay, later we will see more detail on the common configuration of LED. Okay, so this is another how to connect the LED to what we call here to our ports. Okay, you're going to connect your LED, 8 LEDs to your port B. So what you're going to do, you need to have 8 LEDs lah. Okay, so all these 8 LEDs are connected to your port B, and since this one here we use a common anode. Okay, so all the anode of the LED will connect it to 5 volt, and make sure that you have a resistor between your LED to limit the current so that your LED will not damage. Okay, so this is the connection here. You have 5 volt resistor with a 330 ohms. Okay, and then your LED, and this LED are connected to your port B. Okay, so this is the symbol. Okay, this is the circuit diagram, how to connect the LED to your Atmega 32. Okay, so since this one here, you see the positive terminal is connected to, all the positive terminal of LED is connected to VCC, so we know that it's a common anode. Okay, so and then the negative terminal is connected to your ports. Okay, so this is an example of the circuit diagram. And let's look at the LED examples. So write a program to count out and show the result of counting by display at 8 LEDs that are connected to port A. So I think this one we already do it in the earlier slide. Okay, so you have a LED Now, these LED are connected to port A. Okay, which is, okay, so this is your LED. Okay, you have 8 LEDs here connected to port A. Okay, so now what happens here is you're going to do a counting up, okay, which is you're going to count from 0 to FF and display it to your LED. So this is how you're going to do it by using assembly language. And here is you're going to do it by using the what we call C programming. Okay, so in C programming, okay, you just include this file here. Hashtag include avl/io.h. Okay, this one no need to include also, okay. Okay, the define f_cpu 1 million. Okay, means that you're going to define your CPU so that your clock frequency is 1 megahertz. And include util delay.h. Okay, what this function do? Okay, since this one here, we're going to use a delay. Okay, delay function inside of the, okay, to generate a certain delay, so we need to include this file here. Okay, util/delay.h. Okay, if not, we cannot use this delay function here. Alright, so this is your main program. Okay, since your main program is port A is connected to LED, so you need to initialize your port A as an output port. So DDRA equal to OXFF. And then this one here, unsigned char counter. Okay, means that because you use a counter variable here, okay, so you need to declare your counter as an unsigned number and the counter value equal to 0. Okay, and then you have a while loop here. Okay, which is while loop is you're going to do it forever, continuously. Okay, and then port A equal to counter, means that port A sama dengan counter value. Okay, since the counter is 0, so the port A will get a 0 lah. So the first sequence is port A 0, 0, 0, 0. So what happens? All of the LED will turn off. And then counter equal to counter plus 1. Okay, so it will increment 1 every time this loop. Okay, okay. It will increment 1 at one time. Okay, so counter sama dengan counter plus 1. So what happens here? Now counter equal to 1. And then you call a delay. Why we need to call a delay? Because we're going to, okay, because it is a very fast, okay, and we're going to display, we're going to see the LED blinking. So in order to see the LED blinking, we need to put a certain delay. If we not put a certain delay, then what happens is we cannot see the LED blinking from 0 to FF. Okay, why? Because it is too fast. Okay, we cannot see with our naked eye. So that's why we need to, okay, to call a certain delay in order to see the blinking from counting 0 until FF. Okay, so this loop will keep doing forever. Okay, so this is for the LEDs. Okay, next we're going to see the 7-segment display. Okay, there are applications where you need to display a decimal digit using a 7-segment LED display. Okay, so the display could represent the number of the time a switch was pressed off, or you can display the counting sequence by using the 7-segment. Okay, so in this 7-segment, you can display digit 0 to 9 and a hex A to F by using the proper 7-segment codes. Okay, so this is the 7-segment display. Okay, the 7-segment display actually have 8 LEDs. Okay, they are connected together. Okay, which is this 8 LEDs is labeled by A, B, C, D, E, F, G, and H. Okay, so we have 8 kesemuanya, A, B, C, D, E, F, G, and H. Okay, So, okay, so this is the table. Okay, the code that will generate what we call here a value that you're going to display to your 7 segment. For example, okay, so you're going to display 0 to your 7 segment. So what code that you need to put to your 7 segment here is, okay, so usually A is connected to your least significant bit, while H is your most significant bit. Okay, make sure that A is connected to your least significant bit. Okay, this is A, B, C, D, E, F, G, H. Okay, now we're going to display 0. Okay, to display 0, so what value that you're going to give out? Okay, what are the code that you're going to give out to your micro:bit so that this 0 will be displayed on 7 segment? Okay, since you're going to display 0, the LEDs that should be turned on is A, B, C, D, E, and F. Okay, so A, B, C, D, E, and F. What about the rest? The rest. Okay, so this is only valid if you use a common. Okay, common cassette. Okay, if you use a common NF, then the value, okay, will be different lah. Okay, so this one need to become 1, and the rest here become 0. So the codes here will be different according what common configuration that you're going to use, either a common cassette or a common NF. Okay, so make sure that every time you read a question, okay, make sure that you need to identify what common configuration that you use for the 7 segment display as well as your LED. Because the value that you're going to send out in order to display a certain character will be different from common cassette and common NF. Okay, so this is to display 0 lah. Let's say if you're going to display number 2. Okay, so this is number 2. Okay, so number 2, A, B, C, D, E, F, G. So for the number 2, for a common cassette, the value that you need to send out here is A, B, C is 0, D is 1, E is 1, F 0, G 1, and H 0. So this is for the common cassette. If you use a common NF, so what happens here? Okay, so the number will be inverted. Okay, so this will become 1, 0, 1, 0, 0, 1, 0, 0. Okay. Okay, you can see this table here, okay, or you can refer to this table for and see it for understand how to derive the code to display a certain characters here. Okay, so as I mentioned earlier, okay, there are 2 types of common in 7 segment display. One we call it a common NF, and the other one is a common cassette. Okay, which is for the common NF, okay, all of the positive terminal of your LEDs are connected to VDC. Okay, to make the LED on, okay, you need to give 0. Okay, put 0, then your LED will on. Give 1, LED will turn off. Okay, and for the common cassette, okay, so all of the cassette will connected to your ground. So what happens here? Every time you're going to turn on your LED, you need to give 1. Okay, give 1, LED turn on. Give 0, LED turn off. So this is a common cassette and common NF configuration. So this is your LED. Okay, you see here for the common cassette, all of the cassette. Okay, so this is a cassette. All of the negative terminals here. Okay, you see are connected to ground. While common and net, all of the positive terminal, okay, so this is a positive terminal, are connected to ground. Okay, and then you have this is your H. Okay, this is your H. The DP here is actually your H. DP is decimal point. Okay, this is your H. Okay, sometimes we call it as a DP. Okay, and then make sure that the arrangement here is correct lah. Okay, don't do A, B, C, D, E, F, G, H. So this is wrong. Okay, A must be your LSB, while H is your MSB. Okay, if you write something like this, then your answer will be wrong. Okay, so this is another how to connect LED by using a common cathode and common anode. Okay, you see here, for the common cathode, all the negative terminal are connected to ground, and positive terminal go to your micro P ports. Okay, while the common anode, all the positive terminal are connected to VCC, while the negative terminal connected to your microprocessor port. Okay, so let's look at the. Yeah, saya.
I have a question.
Yeah.
Where is the location of hash again?
Location of H.
Yeah.
Okay, H is at bit 7. Okay, here, this is your H. Decimal point should be there.
Decimal point. Okay. Thank you, sir.
Okay, so let's look at the example here. Okay, so the 7-channel display could be attached to AVR as below. So this is your Atmega 32, and this is your 7 segment. And you see here, this 7 segment here, you use a common cathode or common anode. Okay, you see the ground. Okay, so every time you see the 7 segment with a ground, you know that this is a common cathode. Okay, for the common cathode, to turn on, you need to give a 0, and to turn off, you need to give. Okay, sorry. Common cathode, turn on, give 1. Okay, and 0, turn off. Okay, so now, okay, so this 7 segment, you have A, B, C, D, E, F, G, and decimal point. And this 7 segment here is connected to your port B. You see here, A connected to PB0. Okay, because this is your LSB. So that's why A connected to your PB0, and decimal point, your H is connected to PB7 because this one is MSB. Okay. So now, this is the value that you set out to your port B. Okay, actually you write something like this lah. Port B equal to 0B00111111. So now you're going to see what are the characters that will be displayed to your 7 segment. Okay, since this 7 segment is a common cathode. Okay, so what happens here? Every time you give 1, the LED will turn on. Okay, so now first we identify the location of our A, B, C until decimal point. So this is your A, B, C, D, E, F, G, and H. Okay, and then this is your 7 segment. Sorry. A, B, C, D, E, F, G, and this is your H. Okay, so this is the value that you set out your port B. Port B equal to 0B00111111. So now we're going to figure out what are the characters that will be displayed display on the 7th segment. Okay, assume that the common character is used in this example. Okay, so the common character, it says that when you use a common character, the LED will turn on. So what happened here is, okay, LED A turn on, B also turn on, C turn on, D turn on, E1 also turn on, F1 also turn on. What about G and H? Since G and H is 0, 0, so this one will turn off. So what would be the number that will be displayed to your 7th segment? It will display 0. Okay, I change this one here. Okay, now instead of using a common character, now we use a common NN. Okay, so what would be the character that will be displayed? Okay, if we send the same numbers here. Okay, the same number we send it, but now we use a common NN. Okay, so this is a common character, and now we're going to investigate what are the characters that will be displayed when we use the common. So A, B, C, D, E, F, G, and H. Okay, so now for the common NN, we know that if you give 0, then LED turn on. If you give 1, then LED turn off. Okay, so what happened here? So A1, so this is turn off. B also 1, turn off. C1 turn off. D1 also turn off. E and F also 1, turn off and turn off. What about G? Okay, G turn on. What about H? H also turn on. So this is the character that will be displayed on your 7th segment if you use common NN with the same value to your port bit. So that's why I'm telling you, okay, the common configuration here is crucial, okay, in order to determine what are the number that will be, or what are the characters that will be displayed to your 7th segment. Okay, so let's look at another example. Okay, so 7th segment is connected to port C. Okay, write a code that will display 1 to the 7th segment. Okay, you're going to display 1 to your 7th segment. Okay, now you're going to write a program. Okay, so before we write a program, first we need to identify what are the segments, what are the common configuration that we will use on our 7th segment. Okay, so let's say like in this case, we are using a common cassette. Okay, so this is connected to ground. So this is a common cassette. The common cassette means that 0 turn on and 1, common cassette 0 turn off and 1 turn on. Okay, so now you're going to display 1. So this is a 1. Okay, so you draw your 7th segment A, B, C, D, E, F, G, and H. Okay, 1 is here lah. Okay, this is 1. Okay, so you need to find out what are the value that you're going to send out. So A, B, C, D, E, F, G, and H. Okay, since this is a common cassette, okay, to turn on, we need to give 1. Okay, so B and C must turn on. So B and C get 1, while the rest get 0. So this is equivalent to 0, 6 in hexadecimal. Okay, now we're going to write the program. Okay, so started with hashtag include avr/io.h. Okay, and then start with your int main void. Okay, start your main program, open clear bracket and close clear bracket here. Okay, so first thing first, what you're going to do? Okay, so this is our Mega 32. Port C connected to your 7 segment. So what you're going to do to your port C? We need to initialize port C so that it becomes output port. Okay, once it becomes output port, then we can use. Okay, it can use it to send this number to the 7 difference so that it will display number 1. Okay, so initialize your import port first. Okay, so DDRC equal to OX FF. So what happened here? Port C sama dengan output port. Okay, next, you're going to set out this value. Okay, we're going to display 1 to 7 segment. Okay, so what value that you're going to send to your port C? So this is the value that you're going to send out to your port C. So you can simply write port C equal to 0B. Okay, if you're going to use a binary number, 0000 0110, or you can use the port C equal to OX06 if you're going to use the hexadecimal number. Okay, so all these two actually give the same answer, which is it will display 1 to your 7 segment display. Okay, so this is an example. And then we have another example. Okay, so another one here. Again, the 7 segment is connected to port A. Write a code that displays 3 on the 7 segment. Okay, so now you're going to display number 3 to your 7 segment. Okay, so first what you need to do is you need to find out what are. Okay, this one here is a common. Okay, so I just tukar lah. Okay, we use a common cat. Okay, so this one is common NN. Okay, so common NN 0 on 1 off. Okay, now I'm going to display number 3. Okay, so A, B, C, D, E, F, G, H. Okay, so I need to identify what is the value that I'm going to send out to port C so that it will display number 3. Okay, since I use a common NN, so what happened here is common NN, when I give 0, the LED will turn on. So according to this one here, so this is the number that I'm going to send out. So this is A, B, C, D, E, F, G, and H. So A, LED turn on, so get 0. B also turn on, 0. C 0. D 0. What about E? E turn off, so get 1. F turn off, get 1. This also 0 and this 1. So this is the number that I'm going to send out to my port C. Okay, so now write the program. Okay, hashtag include avr/io.h and then start with main program. Okay, open clear bracket and close clear bracket. Okay, so first, what you're going to do, initialize port C so that the port C become output port. So DDRC equal to OXFF. And then next, send this value to your port C so that it will display number 3. So port C equal to 0B. Okay, just use the binary number 10110000. So this is the value that I'm going to send out in order to display number 3 if I use the common NN. Okay, if I use the common cassette for Wi-Fi, so I need to use this number lah in order to display number. Okay, any question up until here? Okay, if no question, I think we stop here. Okay, and then the next the remaining slide we continue on the next week. Any question, guys?
No, Doctor.